Welcome to the third Dialogues on Boundary Current Systems, organized by Ocean Observations Physics and Climate Panel. The focus today is the Kuroshio system. My name is Eitarou Oka from University of Tokyo, and I'm going to talk about observations in part 1. Kuroshio is the western boundary current of the subtropical gyre of the North Pacific Ocean. It's bifurcated from the North Equatorial Current east of the Philippines and enters the East China Sea east of Taiwan and exits the East China Sea through the Tokara Strait south of Kyushu. It then flows eastward along the southern coast of Japan and passes over the Izu-Ogasawa Ridge and leaves the southern coast of Japan to be a Kuroshio extension in the downstream region. In the East China Sea and further upstream regions, the Kuroshio flows along the continental slope with relatively small variability. In contrast, in the southern region of Japan, the Kuroshio has a bimodal path, which are the large meander path and the non-large meander path along the coast. Such path variations have impact on the local fisheries, shipping, etc. And recent studies also show that such path variations have an impact on the Kuroshio extension in the downstream and also the local climate in coastal region of Japan, as I explained later. After leaving the Japanese coast, the Kuroshio extension is a free jet flowing over the deep sea floor and is characterized by large mesoscale variability. Today, I'm going to talk about what sustained observations have been conducted and used to understand the variability of the Kuroshio and the Kuroshio extension. I will introduce the history of the Kuroshio studies using tide gauge data and the satellite altimetry sea surface height data supported by shipboard observations. I will also introduce coastal and other observations. First, I introduce studies using tide gauge data during the 1980s. This figure shows the lowest latitude of the Kuroshio in the southern region of Japan. Through the late 1970s through the 80s, the Kuroshio frequently took a large meander path and such path variations are studied intensively. And it's led by Masaki Kawabe, a former OOPC member. At that time, we didn't have satellite altimetry data, so the tide gauge data along the southern coast of Japan or on some islands are the precious time series data. Whether the Kuroshio takes the large meander path or a non-large meander path is well monitored by sea level difference between Kushimoto and Uragami number 6 and 7, which are only 15 kilometers apart. The sea level difference between these stations are small when the Kuroshio takes a large meander path. Furthermore, the sea level at the Miyake-jima and Hachijojima Islands, using these sea levels, the non-large meander path of the Kuroshio is further classified into nearshore type and the offshore types. So there are 3 typical paths of the Kuroshio, and Kawabe examined the sea level data to examine the transition cycle among these 3 paths. And during the 80s, also the tide gauge data on both sides of the Tokara Strait or in the Tokara Strait are used to monitor the velocity, volume transport, and the meridional position of the Kuroshio in the Tokara Strait. And the relation between these upstream conditions and path variations of south of Japan was examined. However, at that time, we didn't have clear conclusions. And Dr. Miyazawa will talk about the mechanism on large meander generation obtained by recent modern studies in part 2. Since TOPEX Poseidon altimeter was launched in fall 1982, studies using altimetric sea surface height data are increased, and the research target gradually shifted from the Kuroshio to the Kuroshio extension. This was because the Kuroshio large meander did not occur after 1992. The Kuroshio extension studies using SSH data was led by Bochu, who found the pronounced decadal variability of the Kuroshio extension between unstable and stable states in their 2005 paper. This decadal variability of the K system is forced not by the overlying wind, but by the PDO-related wind stress variability in the central North Pacific. In the warm phase of the PDO, when we have stronger westerlies and stronger allusion low, negative sea surface height anomalies are generated in the central North Pacific and propagates westward as volcanic Rossby waves. And when these sea surface anomalies arrived east of Japan after 3 to 4 years, the Kuroshio extension became unstable. On the other hand, in the cool phase of the PDO with weaker westerlies and allusion low, positive sea surface anomalies are generated, which makes Kuroshio extension stable after 3 to 4 years. So when Kuroshio extension, for example, is unstable, its path is longer and the Kuroshio extension is weaker and it takes southerly position and its southern recirculation gyre is weaker. So using these 4 K-related properties, Bochu defined K index for the unstable and stable states of the Kuroshio extension. And this corresponds very well with the PDO index with the time lag of about 3 to 4 years, a time needed for the Rossby wave propagation. You might think why the Kuroshio extension is stable when positive sea surface height anomalies are arriving and vice versa. And the key is the Kuroshio extension, Kuroshio's position over the Izu-Ogasawa Ridge here. And when positive sea surface anomalies are arriving, the Kuroshio extension is in its northerly position, and then the Kuroshio passes over the deep gap of the Izu-Ogasawa Ridge. On the other hand, when negative sea surface anomalies are arriving, the Kuroshio extension is in the southerly position, and the Kuroshio passes over the shallower segment of the Izu-Ogasawa Ridge, which likely generates large amplitude meanders. Such decadal Kuroshio extension variability has large impact on water masses and properties and AST interaction. I don't go into details, but the one example is that the stable Kuroshio extension with higher sea surface temperature and stronger SSH front enhances upward turbulent heat flux in the downstream region, which induces a poleward shift in storm tracks. So it has a variety of consequences. A recent topic of the Kuroshio is that the large meander occurred since August 2017 after 12 years of non-occurrence. And the large meander has continued for nearly 4 years, which is the second longest observed large meander next to the 1975 to 80 period. One is its important consequences that the termination of the wind force indicator K variability. So the Kuroshio extension switched from the stable to unstable state in mid 2016, and it was expected to stay in unstable state for the next several years from the PDO index. But the extension unexpectedly switched back to the stable state in mid 2017 when the large meander began. So this is because when the Kuroshio takes a large meander, it passes the when the Kuroshio takes a large meander path, it passes over the northernmost part of the East Ogasawa Ridge, and which stabilizes the Kuroshio extension path in the downstream region, as I mentioned earlier. Thus, the wind force decayability of the Kuroshio extension that has lasted for the last 25 years suddenly terminated, and now Kuroshio extension is in large meander force stable state since mid 2017. Next, I'd like to mention repeat Hydroflex sections by Japanese agencies. The most representative one is the 137-degree east line maintained by the Japan Meteorological Agency, which has lasted biannually for more than 50 years since 1967. This section crosses the major currents in the Western North Pacific and collects not only physical properties, but also chemical and biological properties, as well as marine pollutants, etc. And in addition to this 137-degree section, the other JMWA sections crosses the Kuroshio in the East China Sea or in the Tokara Strait, south of Japan, as well as south of Ryukyu Islands, where the northeastward Ryukyu currents was found about 20 years ago. And the data from these JMWA cruises were open publicly through the JMWA website and have been used by many scientists of many countries. Here the example, Go et al. 2013 estimated volume transport and nitrate transport by the Kuroshio and the Ryukyu current using these sections, repeat Hydroflex sections, and the inverse method. Sugimoto et al. 2010 examined the decayed variability of the volume transport of the Kuroshio across the 137-degree section and its relation to the PDO. And I like to emphasize that besides these studies, the shipboard data have supported other studies using, for example, tide gauge data or satellite data or modeling studies. Other Japanese agencies also have conducted shipboard observations. For example, the Japan Coast Guard had conducted Hydroflex sections along the 144-degree east for 30 years, but stopped it about 10 years ago. The Japan Fisheries Agency also conducted O-line along 138-degree east 5 times a year since 2002. Next, I'd like to introduce coast observations inside Kuroshio. So this figure shows that there are very surprisingly high dense repeat Hydroflex sections by prefecture fisheries research institutes. These data are open with some delay through Japan Oceanographic Data Center, and more easy access is expected. In addition to the Hydroflex sections, recent studies use high-resolution satellite data for the studies of the Kuroshio and the coastal currents. GCOM-C by JAXA has very high spatial resolution, and Himawari 8 by JMWA has very high temporal resolution of 10 minutes, which realizes seamless daily distribution of temperature and chlorophyll. So these are the one example, so showing surface chlorophyll daily distribution south of the along the southern coast of Japan, and which shows that cyclonic circulation develops in Suruga Bay here. So the Kuroshio has a impact in coastal regions, and Kuroshio frontal variability has impact in the such coastal currents. And in the near future, we should be also be able to study the impact of the such coastal conditions to the Kuroshio. And recent studies also use the satellite data to examine the influence of the Kuroshio large meander on the local climate in coastal regions. So it was previously believed that the cyclonic circulation associated with the large meander is accompanied by lower SSD, but actually the westward flow bifurcated from the Kuroshio large meander advex brings warm water to the coastal region and increase the sea surface temperature by 1 to 3 degrees Celsius, like this. And numerical experiment shows that it increases the air temperature in Kanto area, including Tokyo, by 0.6 degrees Celsius. So last summer, we had a historical record of 41.1 degrees Celsius in Hamamatsu City in Tokai area. So this historical record is probably partly contributed by the Kuroshio large meander. And was the same research possible in the previous large meander period, or about 15 years ago? So with the modern sea surface data, the warm water intrusion is also visible in May 2005 when the Kuroshio takes a large meander path. But at that time, the latest sea surface data was OISSD, which shows nothing like that. So such research was impossible at that time. Finally, I briefly mention other observations. The Japan Coast Guard has operated several wave gliders in the Japan Sea and near the Ryukyu Islands, and contribution to the surface heat flux measurements is expected because we have only one keel buoy of NOAA near Kuroshio. Some studies use pressure sensor data of seismometers deployed along the Nankai Trough, where we expect huge earthquake in the near future. So Nagano et al., this study in Nagano et al. 2021 used the pressure data to see the changes of surface and deep circulation associated with the development of large meander. HF radar is for the Kuroshio is operated by Miyazaki Prefecture, southeast of Kyushu since 2018. And the last operational observation using glider is almost, we don't have any in Japan. because there are some reasons, but the biggest reason is that there are too many fishing nets around the Japanese coast all over the country. So it greatly limits the opportunities for development and recovery of gliders. Okay, that's the end of my talk, and I hope to see you on the webinar on July 6th. Thank you.